Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet, drawing Diels Alder transition states, the endo effect. Okay gang, so at this point, if you're watching this video, that means you've made it almost completely through conjugated systems. Congrats. So you're looking at Diels Alder transition states, and maybe you tried the worksheet that this walkthrough is corresponding to. Well, hopefully we can demystify any transition states that maybe cause some confusion, and maybe more likely the last problem, we can go through that because I think it might, put everything we know about Diels Alder reactions to the test. So let's do it. Okay gang, so 4 total problems on this worksheet. 1, 2, and 3 are going to be, we have a Diels Alder handed to us on a silver platter, right, with the product included. All we need to do is draw the transition state. So problem 1 is one of those 3. So if we take a look here, right, if we just make sense of our surroundings, I think what you can see is we have our diene, we have a dienophile, we have our product, we see plus an enantiomer, and I think you can see, because I know you're Diels Alder pros by now, right, we have this electron donating group. Through resonance, this will cause a negative charge down here. Just a little review. And we have this lovely electron withdrawing group right there. We know it will suck electrons out of there, so we have our positive end down here. We have all of our, electronically we are matched up. And in terms of honoring the endo effect, right, we know that we have out groups and in groups. We like to put our electron donating groups as out, and we also like to put, well, actually the bigger stipulation is that our electron withdrawing groups are going to be out groups because of the fact that they will contain sp or sp2 hybridized atoms. Those have p orbitals. In the transition states, we will draw the p orbitals in our diene will interact with the p orbitals of our electron withdrawing groups in the dienophile. It will stabilize the transition state. That is the endo effect, right? Okay, and obviously the in and out rule is a trick we use on paper. The transition state explains, why these things align the way they do in space. So if we take a look at this, we know our charges line up. I'm going to draw my little pocket forming ring. I'll number my carbons 1, 2, 3, 4, 5, and 6. You can do this either way because we do have this plus an enantiomer, but what I'm going to go ahead and do, right, when we draw these transition states, I'm just going to go ahead and do diene over dienophile. I'll draw my diene looking like this. Draw my my dotted lines down like this. I draw 2 carbons with a double bond. I think you can see this kind of hovering over this right there. Okay, so what we can do now, I'll very smallly, or very tinily, I can't figure out the right adjective, but I will label these like such. Just make sure you have 1 connecting to 6, 4 connecting to 5, or however you number on your structure. Just make sure you number correctly, right? Going from here to here. Okay, so now let's fill in the groups on our diene. So we can see here that this OCH3, as we slide across, it's not going to be sticking over top, it's an out group. So the in groups will stick out like this. I'm going to draw this hydrogen that is not shown here, but I'll show you how that kind of sticks over top over here in space. So the OCH3 has to be somewhere like this. Use your best, this is where, the artistic people thrive, and myself, I don't thrive. So nothing on 2, nothing on 3. On 4, we have an in-methyl, right? So we have a hydrogen that's going down like this. That hydrogen will look something more like that. The methyl group's going to boldly stick out like this. So, same direction as this hydrogen. If you can see that the methyl group and the hydrogen are both in, they're both going to stick out like that. Now's where we need to reflect the endo effect. So if we look at our dienophile, we see that across this double bond right here, I'm going to go ahead and erase these. We see that the nitrile and the methyl are trans to one another. They will not be on the same side of this double bond. Now the question is do we want to put the cyanide underneath the diene or out over here? Is it going to be in this space or in this space? And because of the endo effect, we are going to put the nitrile underneath. Because when the diene is starting to go over top of our dienophile, or vice versa, the p orbitals in this carbon, this carbon, this carbon, and this carbon will interact with the p orbitals in the nitrile. Because you can see this is an sp carbon, this is an sp nitrogen. They have p orbitals. Those p orbitals interact as the diene lowers onto the dienophile, or as the diene rises up to the dienophile, and it stabilizes the transition state. So if you're thinking, oh, what about sterics? Get that out of your head, right? This is a p orbital transition state stabilization thing. Same way we saw the p orbitals stabilize the transition state of SN2 reactions or E2 reactions. So because this is underneath here, and again, if you're wondering, and this could be confusing, I know you're saying we have it as an out group, and that doesn't look like that when we slide it over. The in and out group thing is just so we have a convenient convention for assigning stereochemistry, right? This just helps us assign stereochemistry. This is why they end up having the same stereochemistry. Okay, so that means the methyl group needs to be out over here because we need to have these on opposite sides of the double bond. So this is a valid transition state. Hopefully that makes sense. That does it for problem 1. On to 2. Rolling on into problem 2, you can see we have another seemingly straightforward Diels Alder reactions, and don't worry, it is. So when we see what we have going on here, right, I think it's no surprise we see through the resonance, if we do this real quick, negative end is down there, and with this amide, right, this electron withdrawing group, because right off of our system, which is these two carbons, we see we have, you know, this partially positive carbon, it's going to be sucking electron density out of the ring, and we see that via the resonance. So of course I've marked this all up just to show you that the charges are lined up. This is just a problem where you have to worry about drawing the transition state. So let me do a little cleanup. Yada, yada, yada. Okay, so now back to the procedure of actually drawing the transition state for the product we're given, right? So I'll number my carbons, 1, 2, 3, 4, 5, and 6. Draw my little pocket with the ring forming. And again, I'm going to do diene over dienophile. If you wanted to do it dienophile over diene, all you really need to do is if you draw one picture, just move one thing above the other. It doesn't make a difference. So I like to draw my little slanted diene like this. You can see carbon 1, 2, 3, and 4. Then I like to do my drop a dotted line, so you have a slant, connect them together with a double bond. There you go. Then you have carbon number 5 and then carbon number 6. Okay. So now that we have, you know, diene hovering over dienophile, now we need to just fill in our groups and we're done. So remember this, because of the endo effect, your withdrawing group, the thing with a lot of p orbitals, is going to want to be underneath your diene. So even if we start off with 6, let's start off with 6 this time. I have a choice. I either have to put the amide over here, and I'm just writing the word amide, or I put the amide underneath. And I know that's like really bad perspective. I just can't. Maybe I can do this a little bit better. Something more in the lines of like this. Yeah, just to show you that it's really in this space underneath. And we know that the p orbitals in this electron withdrawing group like to interact with these p orbitals in the transition state to help for stabilization purposes. So we will not put the amide over here. That's actually for the exo product. That's called the exo effect, and that's not the product you get. That's not the major product. It's the endo product that is the major. So NH2, nothing on 5. We don't have to worry about that. I'll reconnect. So then on 1, right, we have the hydrogen. I'll draw that in for completeness. That's, you know, exo, and it's this O-ethyl that is going the same way as the amide, which is why they have the same stereochemistry. And on 4, right, we have a similar thing going on. It's an out group just like the O-ethyl. There is a hydrogen here. That will go there as well, facing the same way as that hydrogen. Okay, gang, yeah, these hydrogens are optional. So if you're wondering why I didn't have those in the answer key, it's just because they're not needed. Just for emphasis, just for the extra explanation that you VIPs get for being great geochemists. Okay, so this is the transition state for 2. Let's do 3 and then getting closer to that meaty problem 4. Okay, gang, tackling problem 3. We take a look right here and we see we have one of those lovely dienophiles where, it's symmetrical. And I know I'm handing you these problems, you're just drawing the transition state, but it's one of those things right here where you don't have to worry about charge alignment if you see this in any other Diels Alder problem, right? And then we have this diene right here. We see we have an electron donating group. Just for completeness, we know the negative end would wind up top here, but we're not really worrying about that. That was just, extra discussion. So, transition state. We'll draw a little pocket of formation. I'll number my carbons 1, 2, 3, 4, 5, and 6. Nothing changes. Don't be thrown off that this is, a cyclic dienophile. Nothing is going to throw us off. So I will draw my diene like this. I'll do my slanted line, connect the dots, okay? So I will number 1, 2, 3, 4, 5, and I'm gonna number on this side actually, you'll see why, 5 and 6. Okay, so let's tackle the dienophile first. So I think you can see we have 2 groups and they're on the same side of our double bond, right? And that makes sense because it's a ring. You can see that these are both electron withdrawing groups. They both have p orbitals, right? So these are the things we want to make sure are underneath our approaching diene, right? Because of the endo effect, because of the p orbitals wanting to interact with the p orbitals in our diene to stabilize the transition state. So we need to have them both like this. You can see that they're on one side of the double bond. If I even wanted to reflect the 2 hydrogens on this side of the double bond, right, we know that they would be out, not underneath our diene. They'd be over here. So you can see that this cyclic ester right here, the diester, is going to be underneath right there, the approaching diene, that is. So we just have to fill in our diene groups and then we're good to go. So nothing on 1, and on 2 we have one of these, groups that end up planar. So you just need to really attach it. Don't really worry about reflecting any type of, spatial orientation or anything like that. Just stick that ethyl group on. It just needs to be on carbon 2. Okay, well, 2 and how I've numbered here. Now on 4 we have the NH2, and we know it's an out group. It's going to be facing like this. It's going to be facing the same way as the electron withdrawing group on the dienophile. So this is the transition state for problem 3. And if you're here for problem 4, don't worry, we're getting to it next. And hopefully clear up any issues you may have had with it. Okay, gang, problem 4 is a little bit different than its predecessors 1, 2, and 3. So if we take a look at this Diels Alder reaction we are presented with, we are shown, you're right, we have the reactants, and then we're shown 2 products. And we are told that one is the endo product, right, the one we've come to know and love, the one that we know has that great stabilization from the p orbital overlap between the electron withdrawing group on the dienophile and the conjugated system on the diene, and the exo product, which is not that. So we haven't really talked about the exo product all that much, but really you just need to know that it's the opposite, it's just the opposite alignment of the dienophile when your diene attaches to it. So if we take a look here, some noticeable differences off the bat that I want to point out before we draw the transition state, because sometimes you'll get a problem like this and people dress it up or they misalign some of the pieces to help to try to confuse you. So if we take a look right here, I think you can see, right, if we try to just connect our pieces right off the bat, you'd see that if we numbered 1, 2, 3, 4, 5, and 6, that's not how we end up in the product. You can see that this CO2 ET, which if I redrew this, is just an ester, but that syntax is used very, very commonly, especially in jOeCHEM 2, to abbreviate esters. If we take a look over here, right, we see that, in fact, that is, sorry gang, I have a typo. This should be an ET. Not that that changes anything about the problem. ET, sorry about that. Okay, so that's actually on carbon. This would, based on how we connected right here, that would say carbon 5, but in fact, it looks like it's on carbon 6. So the first thing I want to just go over and just look at real quick if I just have this drawn right here and this drawn again right here, OME, this T-butyl group. So I think you can see from the resonance on the, if we were going to do our charge alignment, on the diene, we get the negative at the bottom. And on the dienophile, right, we're dealing with these two carbons. I think you can see that the electron withdrawing group puts the positive charge right there. So in fact, this is not how we align up top. We need to flip one piece to make sure our charges align. So this looks like this. Whoop. So I'm just going to flip my dienophile like a pancake, or just flip it vertically. CO2ET. Okay, now if you check this and we line these up, you'll see that they, in fact, we see our ester on 6, the methyl group on 5. Okay, so now the real question is, which is the exo and which is the endo? Well, hopefully when you see this, a light bulb went off in your head, and you know how we always try to put our electron withdrawing groups, or we do put our electron withdrawing groups as out groups, right? Because that helps us predict the stereochemistry that we know the transition state explains, right? So let's draw the transition state, and I'll show you how the transition state will indicate to us which one is which. Okay, so we know we are used to drawing the endo transition state. We know that's the major product, right? We just need to find it up top. So I'll draw my diene, I'll draw my dienophile. Now on carbon, here I'll label 1, 2, 3, 4, 5, and 6. So we know on carbon 1 we have our O-methyl, and that's going to be an out group. We know the way it's facing is not over top of the dienophile, like the hydrogen there would be pointing. Nothing on 2. We know 3 is one of those planar groups. Just going to stick it on. It's just going to hang out and watch everything unfold. Now on 5, right? This is where we're working with this because of the charge alignment. We need to figure out on, between this ester and this methyl, which one is under, on which one is on which side of this dienophile. And we know because of the endo effect, we want that ester to be underneath. It needs to be in on the action so that its p orbitals, right? We know it has p orbitals because that ester looks like this. I'll put an R there. We know sp2. It's going to, for the endo effect, for that good stabilization to kick in, we need these p orbitals to be underneath the conjugate system in our diene. And that means, because this is a trans relationship between the methyl and the ester, the methyl will be over here. So this is the endo effect. We know this is the transition state that will give yield to the major product for us. Now, where is that represented here? Well, remember, because of that, we know that these two have the same stereochemistry, right? And the methyl will have opposite stereochemistry because these are both facing the same direction, right? This hydrogen over here will have the same stereochemistry as this methyl group. So if we look up our product, hopefully you can see this methoxide and this ester have the same stereochemistry in this product right here. So this is in fact the endo major product, and if you want to, you could say p orbital stabilization, which means this is the exo product. And as a bonus, I will draw you the exo transition state as well. So I'm going to go ahead and erase this real quick. So I'll do this in purple. So this is for the minor product, or the not nearly as formed product, compared to the endo. So this is exo. And nothing changes on the diene, right? Business as usual. It's really the alignment of the groups on the dienophile. So instead of this, we're just going to flip what we have. So this is 1, 2, 3, 4, and we have 5 and 6. So the ethoxide, so the ester is now not underneath the diene, and this methyl is underneath. So you can see the trans relationship between the groups. And we've just really flipped this over like that. But here, you miss out on the wonderful p orbital stabilization for the transition state, because here the ester is not underneath the diene. You miss out. This is the major product, the exo product, which we know and love. This transition state explains why p orbital stabilization. You wouldn't even have to really write that down. That's just if you felt like it. And I actually encourage you to write less, because sometimes it gets you into trouble and you say something that's not correct and then you end up getting points taken off. But this is how you do problem for the exo product. We haven't really formally talked about it, but now we have it in a problem. You've seen the solutions walkthrough. You're great because you're watching it. Number 4. Gang, thank you for watching this worksheet solutions walkthrough. If you're watching this, that means you've supported jOeCHEM financially, and I'm just want to say thank you for that. I'm so humble you're using jOeCHEM as a tool to help you crush carbon, and I love that you're using it now. I hope that you're using it towards the end of your organic career, and no matter what, I'll see you all in the next video.